Uh, okay, so good evening, everyone. Today I am going to discuss the week 9 assignment 9 of the previous year of this basic electronics course, which is NOC-EE62, and this is the tutorial class. Like every week, this week also I am taking this class, and the instructor is Mohesh B. Patil from IIT Bombay, and I am also a PMRF fellow from IIT Bombay. My name is Subhajit Basak, and today we'll discuss some problem regarding the op-amp. Okay, so let's start. uh, yeah. So okay, so far whatever we have discussed regarding the op-amp circuit, that are the op-amp. At first we have discussed the basic op-amp circuits, basic the basic op-amp circuits, and then we have discussed about some idealities, that is the ideal op-amp, and we have considered the negative feedback. Okay, and then we incorporate some non-idealities in the op-amp circuit. Okay, so basically in the basic op-amp circuits, we have considered the op-amp to be ideal, and also it has some negative feedback, and using these two we have generated or constructed some of the basic circuits, such as inverting amplifier, and also non-inverting amplifier. Then we have discussed about the adder, which is basically the summer. Okay, and then we have done with the subtractor, and then integrator. So like that we have already discussed, and all of these are due to the negative feedback, and then we have discussed about the non-idealities. But today I will discuss a very important and interesting op-amp circuit, which is op-amp in positive feedback. Okay, so today I will discuss the op-amp with positive feedback, and then I will discuss something about regenerative regenerative and degenerative feedback, and then I will discuss about the basic bistable circuit, and then I will discuss making the bistable circuit switching state. That means the bistable circuit, how by using the external input it can switch its own state. Okay, and this is very important thing, which is often known as Schmitt trigger, the Schmitt trigger circuit. Okay, yeah. So at first I will discuss about some degenerative feedback and non-degenerative feedback. So suppose this is a basic op-amp circuit where we have input resistance R1 and output, sorry, and this is the feedback resistance, which is RF, and this is the VO. Okay, and then another thing, so this can be plus, now this is minus, so this goes to ground. This is the basic R1, it is also ground, and now it has something. This is VO output, this is RL. Okay, yeah. Okay, so basically I have drawn two op-amp circuit. This op-amp is in negative feedback, this is in negative feedback. Why negative feedback? Because a part of the output is being fed to the input, so there is a output to input path or the feedback path. So this is the feedback and it is going to the inverting terminal of an op-amp, so it is known as a negative feedback. Okay, but here the out part of the output which is fed to the input, that goes to the positive terminal, that means non-inverting terminal of an op-amp. So this is known as a positive feedback. So this negative feedback is often known as degenerative feedback. Degenerative, why the name is degenerative and regenerative, I will discuss in this lecture. Okay, and this is regenerative feedback. Okay, so the figures show two op amps, one connected in negative feedback configuration and the other connected in the positive feedback condition. So the similarity of these two circuits are that both the cases there is no external input excitation, right? So basically we have grounded both the terminal, right? Positive terminal and the negative terminal. So both the op amps are ideal. You consider both the op amp as ideal with infinite loop gain, that is open loop gain is infinite, and also there is no sink current, that means no current can flow to the op amp, no sink current. Okay, so in the absence of any external input, so suppose this both terminal is affected a small millivolt level noise, so noise is too small, the voltage so small, if both of the terminal, so small millivolt level noise, so noise is present in any of the circuit, so this noise can be easily fed to the input terminal of the op amp. So suppose this small millivolt level noise is affecting the two circuits similarly at a certain point of time. Okay, so in case of the negative feedback also, in case of the positive feedback also. So noise can often refer to as it has a small amplitude, that is the millivolt level signal, and also it has a very high frequency, you can consider it as noise. Okay, so what is happening in both the cases I am discussing one by one. See, so suppose, so here what is the input difference? Input difference is nothing but V plus minus V minus, right? So suppose both the terminals are affected by the noise, then suppose this V plus, suppose there is a noise and it is affecting a certain terminal, so suppose it is affecting the V plus terminal. Okay, so if V plus terminal it is affecting, so that means it is a small, or suppose it's affecting the negative terminal, so this thing is small. Suppose V plus minus V minus, it is a small negative quantity, small negative quantity. Okay, and here VID equal to V plus minus V minus, suppose it is a small positive quantity. Okay, so now whatever we get in the output, that is AOL, that is open loop gain, into VID of the op amp. So what is happening here? So suppose this is a small negative voltage that is applying to this. So if VID is small negative, so due to this the VO, this VO will come as a large negative, and now this large negative part is being fed, is a large negative part is being fed to the V minus. Okay, this V plus minus V minus will become again very small. Suppose there is some V plus and a small amount of V minus, and V plus minus V minus is becoming small negative. So now if there is a open loop gain of an amplifier, if we write it as AOL, then what is happening? So it is being multiplied. So VO is basically multiplied, AOL and multiplied by VID, input difference. So if VID, that is V plus minus V minus, is small negative, this VID for this op amp is small negative, and so as a result the output VO is AOL time VID, and now this VID is small negative, so this VO should be large negative voltage that is applying. And now this large negative voltage, a fraction of this case, a fractional negative voltage is getting add up with the internal positive noise, right? And what is happening? So this is known as a degenerative action, because, so how can I state that here? Yeah, so yeah, so suppose yeah, so VO is large negative voltage. Now the part of some VO is being fed back to the input of the V minus. Okay, this is, if this is known as V minus, if this is known as V plus, then the part of this, that is VO into R1 divided by R1 plus RF, right? This is a simple voltage divider rule, voltage division rule. This part is being fed to the input terminal of the op amp. So this is again a negative voltage. So in this case, a fractional of negative voltage is adding up with the positive with the initial positive noise. So this is known as degenerative action, because the signals adding up in the opposite phase. Okay, yeah, here. But here what is happening? So this is a regenerative feedback in this case. So how here? So if suppose this VO is small negative, if VO equal to VID, so suppose this is a small negative quantity, the same thing. So now it is AOL time VID, and as the input is in here, so what is happening? So it is a large VO is large positive. So this figure illustrates the regenerative feedback, because the fractional of the positive output, this positive output, so it is a large positive, so a fraction of this is being add to the positive noise. So signals are adding up in the phase, so that means it is a regenerative feedback. Okay, so due to degenerative action, VID slowly reduces to zero. So these concepts is already we have discussed, which is virtual short. So the concept of virtual short always holds on the degenerative feedback, but the non-inverting terminal of the potential, the non-inverting terminal potential always stays away from the inverting one. So here what is happening? So these differences becomes much more than the previous. So like this, actually the virtual short concept is never hold in the positive feedback circuits. Okay, so for the negative feedback circuit, the output approaches to zero due to decreasing VID, while in due to increasing VID, here the VO saturates in the positive feedback. Okay, yeah. So what is happening? So suppose so what is happening? So suppose a small millivolt level noise is if affecting both the terminal. So so it is the due to the regenerative feedback, some of the output voltage is being fed to the input, and that is adding up with the noise, and that makes this difference vid, that is v plus minus v minus, even larger than that. So this is a regenerative or regenerative feedback, and due to this vo slowly goes to the saturation. That means whatever we have given this vsat and minus vsat, this dc voltage, so the vo attains plus vsat value or minus vsat value, okay, depending upon this thing. If v plus is greater than v minus, then vo goes to plus vsat, and if v plus is less than v minus, then the vo goes to minus vsat region, okay. Yeah, so this is the basic thing of this, okay. So in case of positive feedback, so op amp in positive feedback, so if the op amp is in positive feedback, so virtual short concepts never hold, okay. And the second thing is vo always saturates, maybe a plus vsat or it may be minus vsat. So the similarity can be found like this. Suppose this is something, okay, and we have a ball above this thing, okay. So this is the positive feedback condition of the op amp. So suppose there is some airflow, so that pushes the ball to here. So if the ball goes to here, it cannot be come back to here easily, if not we put any external input, okay. Similarly, if the air flows like this, the ball will be in here, and this ball will remain in here until and unless we put any external effort or external input to make the ball switching the set from this to this, okay. So this is the basic concept of a bistable circuit. Okay, yeah. So we will discuss one by one case, and we will see that how it is appropriate for the Schmitt Trigger circuit, okay. Yeah, so here in the I will solve the first question, which is, in the Schmitt trigger circuit shown in the figure, the op amp is operating with plus minus vsat plus 10 volt and minus 10 volt, okay. So here we have given plus 10 volt, and here we have given minus 10 volt, okay. So which graph correctly describes the VO versus VI relationship? So I have already discussed in the previous class, VO versus VI relationship is often known as transfer characteristics. So we are always interested about the transfer characteristics of any circuit, okay. So we have to find out the transfer characteristics of this particular op amp. So see, I have already discussed that at first we need to find out that what is the feedback of this op amp, okay. So what is the feedback in this case? So there is a feedback path between the output to the non-inverting terminal of the op amp. So that means it is a positive feedback condition. So in positive feedback, what I have already discussed, that if there is some vid means v plus minus v minus, that is the small voltage that is here, if the here the voltage is v plus and voltage is v minus, if this thing is suppose a small positive voltage is there, then what is happening? So here we are getting VO equal to AOL of VID. AOL of VID, that means this is a large positive voltage because AOL is too high, and that is multiplying with the small positive voltage, this large amount of number. So by this we are getting a large positive voltage, and the part of this large positive voltage is being fed to the V plus terminal only. So this V plus terminal is getting at or getting high due to the positive feedback from the output to the non-inverting terminal of the op amp, right? So this VID equal to V plus minus V minus, this also gets increased due to this so this also increased due to increase in V plus, because V plus is now increased. How it is increased? Because earlier what was V plus, that is being added with the amount of the feedback from the output, right? Now V plus is the earlier V plus plus this output VO into R1 divided by R1 plus R2, that is a certain amount of feedback is there. So this V plus increases, so at a result this VID get increased, and as a result again the VO, that is the output, this gets even increased than the previous one, because now VID is much more positive voltage than this one. So that is again multiplied with a large positive number, so that is a large positive voltage, and that large positive voltage is being again some of this large positive voltage again being fed to the positive terminal, which makes the VID even larger, and like this VO goes to infinite. But in a practical circuit it cannot go to VO cannot go to infinite, so the VO finally saturates. Okay, so if we know the transfer characteristics of an basic op amp or ideal op amp, this is VO, this is VI. So we have already discussed that VO is linearly varies with VI, but after a certain input, VI input, this VO saturates, and what is the value of the saturation? That is the DC voltage that is applying as a bias to the op amp, right? So this is VSAT, positive VSAT, plus VSAT, and this is the negative VSAT, negative VSAT. So similarly if we consider like VID equal to V plus minus V minus, okay, see the things correctly. Okay, so suppose this is a small negative voltage, suppose there is a small negative voltage, that means suppose V plus is less than V minus. Okay, so what is happening? The VO is AOL VID, like the previous case. Here we have already discussed like this. So this is a small negative voltage VID, and it is being multiplied with a large amount of open loop gain, and that makes is a large negative voltage, that is a large negative voltage VO. Okay, so this large amount of negative voltage, some amount of this voltage, why? Because there is a voltage division, certain voltage division. So VO, there is R2 and there is R1, so some voltage division rules we can apply, and we can say that certain amount or certain fraction of this large negative voltage is again fed to the V plus. So that means V plus is now negative, some amount of negative voltage, and as it is negative, so these things, it is reducing, V plus is reducing, that means VID is even getting smaller, and as it is even getting smaller, the VO becomes again large negative voltage than this thing. Okay, and that is again fed to this thing. So like this it can saturates. Okay, it cannot go to infinite, but certainly it go to VO go to minus VSAT. Okay, similarly here also in the previous case VO cannot go to infinite, so it can saturate to VSAT, but this case doesn't hold in case of negative feedback. In case of negative feedback, what happens? So suppose we can say, suppose VID is V plus minus V minus. Okay, suppose we are telling this is a small positive voltage, suppose. Okay, say this is a small positive voltage. Now what happens? So VO, that is the output, it is AOL multiplied with VID. So this is a huge number AOL, and this is multiplied with the positive voltage, that makes VO as a large positive voltage. So the certain amount of this large positive voltage, certain fraction of this large positive voltage is being fed to the negative terminal. Okay, so the negative terminal, because then it has a connection from this to this. Okay, this is a negative feedback, right? Okay, in case of negative feedback, this is negative feedback, and this is positive feedback. Okay, this is the positive feedback. Okay, yeah. So in case of negative feedback, what is happening then? The certain amount or certain fraction of this large positive voltage goes to V plus, so which makes V plus minus V minus smaller positive voltage than previous. And if it is smaller, then next the VID is smaller. Next, this VO becomes smaller than this large positive voltage, okay, and then again it fed to the v minus. So v minus, so vid, v plus minus v minus becomes even smaller. So like this v plus minus v minus often goes to 0, and that goes to 0 means vid is goes to 0. That means whatever the voltage that is in v plus, that appears as a v minus. That is the concept of virtual short. So virtual short concept we can be applied in case of negative feedback, which is known as the degenerative feedback. But the virtual short concept we can never apply to the positive feedback condition, which is regenerative feedback condition, okay. So this thing we have already discussed. Yeah, so this positive feedback, op-amp in positive feedback circuit is often known as Schmitt trigger circuit. So the here what is happening, that the op-amp can be in the only two state, that is either it can be a plus vsat state or it can be a minus vsat state. So if the op-amp is in this two state, it is known as bistable circuit. Bistable circuit. So there is a stability in where there are only two states, either 0 or 1. Suppose if the op-amp is in minus vsat condition, then you can refer to the circuit as 0, and if it is in plus vsat condition, you can refer this as 1. So that means only two states are possible, 0 or 1, plus vsat or minus vsat, right? Okay, so this is the basic concepts of a bistable circuit. So Schmitt trigger is an example of a bistable circuit, and if we apply any input, external input, so that external input can change the bistable circuit condition. That means it can change either the op amp from 1 to 0 or from 0 to 1, that is plus vsat to minus vsat or minus vsat to plus vsat. But any external input is needed. Without any external input, the op amp can either be on the two state, that is either it can be plus vsat condition or it can be in minus vsat. So either it can be in 0 or either or it can be in 1, okay. So this is the basic concepts of the op amp. So now whatever I have already discussed, I am discussing one more time. So suppose this is the thing and there is a ball above it. So suppose if there is any airflow, so this ball falls in this condition, and from here it cannot get to the here in this position unless and until we can apply any external input. So similarly, if the airflow in this ball comes in this condition, and it cannot be transferred to this condition unless and until we provide an external input, okay. So this is the concept of a bistable circuit, okay. So now what is the question? So here in this question we have to find out what is the VO versus VI relationship, okay. Yeah, so to solve this thing, so whatever we have already discussed, that if suppose, so to solve this problem, so yeah, so we must consider what is the value of V plus and V minus, okay. So okay, so yeah, so in this circuit, suppose this V minus is basically VI, this V minus is VI, and V plus, that is this V plus, we can apply superposition and we can find out what is the V plus over here. This condition, this is V plus, if this is V plus, so V plus has certain amount of, with VR. Suppose so there are two input, like VR is there and VO is also there. So if we apply superposition, so in superposition, at first we consider VO as 0, then only the input is VR. So VR, there is R1, there is R2. So simply by using the voltage division rule, we can say VR into R2 divided by R1 plus R2. This much voltage appears in V plus, right? And now in the second condition, superposition in the superposition in the second condition, we consider this VR to be 0 and this VO is applied, right? And there is VO, R2 and R1. So there is a simple voltage divider rule, and that much voltage is appearing at V plus, and ultimately as it is a superposition, it is a linear circuit, so that means V plus will be sum of these two. Okay, yeah. So we have calculated what is V minus. V minus is nothing but this input Vi, and what is V plus. V plus can be determined by the superposition of this VR and the VO. VR into R2 divided by R1 plus R2 plus VO into R1 divided by R1 plus R2, right? So this much voltage is applied. So now how to solve this problem? Suppose, so see one thing, yeah. So how to solve this problem? So suppose case number 1, suppose this VO is at plus Vsat condition, okay, V saturation, because I have already discussed that if in op amp, if in op amp there is a positive feedback, so that means the output can be either in plus Vsat condition or in minus Vsat condition. So in case 1 we have considered it is in plus Vsat condition. So that means this Vi is equal to this V minus is Vi and this V plus is VR into R2 divided by R1 plus R2 plus this is Vsat into R1 divided by R1 plus R2. Now what is happening, this VO is plus Vsat, that refers that V plus is greater than V minus, right? Then only it goes to Vsat. But if we give the input like this, but that is if V plus is less than V minus, then only the VO goes to minus Vsat. So this is the switching condition, that is if V plus is less than V minus, then only VO will be minus Vsat from plus Vsat. So using this equation we can write if VR into R2 divided by R1 plus R2 plus this is Vsat into R1 divided by R1 plus R2 is less than Vi, then only this VO will be minus of Vsat. So what is the value? So what is the value of VR? VR is 3 into R2 is 9.2 divided by 1.2 plus 9.2 plus this Vsat. Vsat is what? It is already given plus 10 volt. Okay, so this is plus 10 volt, that is this is a 10 volt into R1, that is 1.2 divided by 1.2 plus 9.2 should be greater than Vi. Okay, that means if we use the calculator, that is 9.2 divided by 1.2 plus 9.2, so that is, yeah, into 3, so this is 2.65 plus 3 into 9.2 divided by 9.2 plus 1.2, yeah, 2.65 and plus 10 into 1.2 divided by this is 10.4, right? Yeah, so this is 10 into 9.2 plus 1.2, yeah, so this is 1.15, this is less than Vi. So that means if Vi is greater than plus 2.65, that is 3.8. So if it is greater than 3 point, so if it is greater than 3.8, so what is happening, if it is greater than 3.8, then V0 will be minus Vsat from plus Vsat, right? Plus Vsat. So earlier it was in plus Vsat, and then if Vi is greater than 3.8, then VO becomes minus Vsat. So similarly, if we follow the case 2, that is case 2, consider VO is initially at minus Vsat condition. So now if if v plus is greater than v minus, then only this v0 goes to plus v sat, right? So that means this vr into r2 divided by r1 plus r2 plus, now it is v0, right? So this equation, this is v0, right? You got it right. In this equation it is v0. So v0 is, now we have considered it is minus v sat, so this is minus v sat into r1 divided by r1 plus r2 if it is greater than this v minus is vi, right? So this is vi, then only it will goes to plus v sat, right? So that means if we write this thing, 3 into 9.2 divided by 1.2 plus 9.2 minus this vsat is, that is plus of minus 10, right? Minus vsat is minus 10 into r1 divided by r1 plus r2, that is greater than vi. That means vi should be less than, this is 2.65 minus 1.15, that is 2.65 minus 1.15, which is 1.5. okay, 1.5, approximately 1.5. okay, yeah. So what is happening in this? So that means, so listen carefully. So if we plot the transfer characteristics of the circuit, that means input versus output, the transfer characteristics of the circuit. So this is input vi and this is output vo. So if it is less than vsat, then v0 goes to plus vsat from minus vsat. okay, so yeah, see this transfer characteristics carefully. okay, so suppose if the input is 3.8, okay, so what is, if the input is greater than 3.8, that means in this region, if it is greater than 3.8 in this region, the output grows from minus vsat. Minus vsat is, in this condition it is minus vsat. okay, from minus vsat it will go to plus vsat. okay, this is go to plus vsat. So this is the thing. So this is, suppose this is plus vsat, that is plus 10 volt, and this is minus vsat. So it will grow from, so I am giving an arrow to indicate this thing. So it will go from minus vsat to plus vsat. Similarly this is 1.5. okay, so sorry, so this is 1.5. 1.5. So similarly here, if vi is less than 1.5, less than 1.5 means in this region, less than 1.5 in this region, then the vo goes to plus vsat from minus vsat condition. So earlier it was minus vsat, and here after 1.5 it goes to, okay, oh, just wait one second. Yeah, so I have done one mistake. Oh, sorry. Yeah. Oh, okay, I have done one mistake. Okay, let's draw the circuit again, the transfer characteristics again. Okay, so suppose this is vi and this is vo and this is 3.8. That means if it is greater than 3.8, then what is happening, it can go to minus vsat from plus vsat. So earlier it was plus vsat, and then it will go to minus vsat. okay, so this is plus vsat, this is the vo plus vsat, and it will go for minus vsat if the input is greater than this. So if we draw some arrow to indicate this thing, so this will be like this. okay, this will be like this. okay, and similarly if it is less than 1.5, that means if it is less than 1.5 in this region, then VO goes to plus Vsat from minus Vsat. So earlier it was minus Vsat, and if it is less than 1.5, so I am using the other pen, okay, other color pen. So it will go from minus, it is go from minus Vsat to plus Vsat. So earlier it was minus Vsat, and then it will go to plus Vsat. Okay, so this is the thing, this is the transfer characteristics, transfer characteristics of the op-amp. Okay, so this thing is known as the hysteresis loop. This loop we can see, this is known as hysteresis loop. So this is the basic memory element. That means, suppose there is a question, suppose if anyone asks that what will be the V0 output, what will be the V0 if Vi is 4 volt, suppose. So 4 volt means if the output is Vi is 4 volt, then we can easily say that output will be minus Vsat, that is minus 10 volt, right? It is minus 10 volt, it is plus 10 volt, right? Plus Vsat means plus 10 volt and it is minus 10 volt, already given in the question. Okay, so then we can easily say VO equal to plus 10 volt. Suppose the question is asked what is the VO if Vi is 1 volt. If Vi is 1 volt means in this region, then we can easily say it is plus Vsat, that means the VO will be plus 10 volt if Vi is 1 volt. But if anyone asks that what will be the VO if Vi is equal to 2 volt, that means it is in between these 2 volt, then what will be the answer? Then the thing is, if Vi is 2 volt, then the output will be plus 10 volt if already the output was plus 10 volt, and the output will be minus 10 volt if already it is minus 10 volt. That means if it is if it was already minus 10 volt, then within this region, the output voltage holds that value. That means the output voltage holds the previous value. So that is the basic concept of the memory, that is the present output is depending upon the past output. Okay, so the present thing is dependent on the past thing. So that means and also if previously it was plus 10 volt, then that will hold this condition. That means it in between this 1.5 to 3.8 volts, the output will depend only whatever in the past situation it was, right? So that is the basic concepts of the memory. So this is this is known as the hysteresis loop, and this is the basic memory element, we can say. So we can use the Schmitt trigger as a memory element. Okay, yeah. So here are some terminology. Suppose this is known as VLT, this is the lower tripling point, and this thing is known as VHT, that is higher tripling point. Okay, and this VHT minus VLT, this is known as hysteresis width. Hysteresis width, the what is the width of the hysteresis curve. Okay, so this is hysteresis curve. Yeah, so this is the basic answer. So so in the given option we can see, so this curve matches with the option B, right? Because this is plus and this is minus. Sorry, so this the right side arrow is downwards and left side arrow is upward, right? Right side is downward, you can see, and left side is upward. So this will be the answer. Okay, okay, one more thing, that here you are seeing this in the hysteresis curve, this arrow is in anti-clockwise direction, sorry, clockwise direction, right? Clockwise direction. So this clockwise direction refers to this is known as inverting Schmitt trigger. Okay, inverting Schmitt trigger. So this inverting Schmitt trigger means the input is applied in the inverting terminal. Here you can see that Vi is applying in the negative inverting terminal. So you can also verify that whether your answer is correct or not. You can always see that in the hysteresis curve, what is the hysteresis loop in which it is in clockwise direction, or what is the direction, actually basically what is the direction, if it is in clockwise direction or anti-clockwise direction. So if it is in clockwise direction, that means it is an inverting Schmitt trigger. That means the input is applying in the inverting terminal of the op amp. And if it comes to anti-clockwise direction, then that means it is a non-inverting Schmitt trigger. Non-inverting Schmitt trigger. Okay, non-inverting Schmitt trigger. So already I have discussed that this is a basic memory element, and this is the hysteresis curve, that is the transfer characteristics curve, and it shows some hysteresis loop, and it is a basic memory element. Okay, yeah. Okay, moving forward to the next question. So what is the VTH of the Schmitt trigger? As I have already discussed, this VTH is higher tripling point, higher tripling point, higher tripling point. So from the diagram we can see this 3.8 is the higher tripling point, 3.8 volt, which is close to option A, right? 3.82 volt. So during actually approximation of this decimal number, so our answer comes as 3.8, so it is close to 3.82. Okay, yeah. So similarly, what is the VTL of the Schmitt trigger of question 1? This is VTL, that means the lower tripling point. Lower, just 1 second. So VTL is nothing but the lower tripling point. So the lower tripling point of using the hysteresis curve, we can see it is 1.5. Okay, 1.5. So it is 1.5. So the correct answer will be option D, right? 1.49. It is close to 1.5. Okay. So this is the basic Schmitt trigger problem and how the Schmitt trigger operates. Okay, yeah. Okay, moving forward to the next part. In the Schmitt trigger circuit shown in the figure, the op amp is operating with plus minus Vsat. Now it is given plus 12 volt and minus 12 volt. That is, it is plus Vsat, which is plus 12 volt, and here it is minus Vsat, which is minus 12 volt. Okay. So now it is being asked that what is the upper and lower trip points. Okay. Okay, so how can we find out? So we first need to draw the transfer characteristics, and from there we can easily say that what is the upper trip point and the lower trip point. So similar is the case. So now see one thing, the input is applied in a non-inverting terminal, so that means in the hysteresis loop the direction of the loop will be anti-clockwise. So at first we will complete the analysis and the solution of this question, and we can also verify that whether the hysteresis curve is that is coming, that is anti-clockwise or clockwise. If it is coming in anti-clockwise, that means that is perfectly matched with our given question, that is it is a non-inverting terminal. Okay, non-inverting op amp. Okay, non-inverting Schmitt trigger. Yeah. So how to solve the problem? I have already solved. So this the process is same. Here the V plus is basically this Vi input voltage. So if we apply a voltage division rule and a superposition, so in superposition VO, at first we consider VO to be 0. So this voltage V plus, this is V plus, and this voltage is V minus. So this V plus will be Vi into R2 divided by R1 plus R2. Okay, and then plus, because the superposition, now consider VO only and consider VO to be Vi to be grounded, so only consider VO. So it will be VO into, using the voltage division rule, R1 divided by R1 plus R2. Okay, yeah. And then V minus is grounded, so V minus is 0. Okay, yeah. So now case number 1. So case number 1, in case number 1, consider VO equal to plus Vsat. At first it was plus Vsat. So that plus Vsat means that V plus is already greater than V minus, that is being amplified, and that's why it is VO is plus Vsat. So now if the V plus is less than V minus, then VO becomes minus Vsat. Okay, minus Vsat, right? If V plus is. So how the V, so what is the value of V plus? It is Vi into, from here we can write, right? this thing. So R2 divided by R1 plus R2 plus this is VO into R1 divided by R1 plus R2 less than 0. So what should be the VI? So VI divided by R2 equal to R1 plus R2 less than minus VO into R1 divided by R1 plus R2. So R1 plus R2, R1 plus R2 cancels out. So that means VI should be less than minus VO into R1 by R2. So that means what is the value of R2? 6.8 and this is 1.5, right? So VI should be less than minus VO we have considered this as plus VSAT in the case 1, right? So it will be VSAT into R1 divided by R2, right? So VI will be less than minus 10 into minus 10 or 12. Here it is 12, right? VSAT is 12. Sorry, so this will be 12. 12 into R1. R1 is 1.5 and R2 is 6.1.5 divided by 6.8. So this comes out to be minus 2.647. Okay. So if VI is minus 2.647, then VO goes to minus VSAT. Okay. Yeah. So this was the case 1. So similarly, if we consider the case 2, so if we consider the case 2, that VO is at first in minus VSAT condition, that means V plus less than V minus, that's why it goes to minus VSAT. Now if this V plus becomes greater than V minus, then only the VO becomes plus VSAT. Okay, so V plus, what is the V plus? From earlier equation you can say VI into R2 divided by R1 plus R2 plus VO into R1 divided by R1 plus R2. It should be greater than equal to 0, or we can write Vi into R2 divided by R1 plus R2 should be greater than of minus V0 into R1 divided by R1 plus R2. These two cancels out. That means Vi should be greater than minus VO into R1 by R2. That means now the VO is minus VSAT. So minus and minus becomes plus VSAT. So minus VSAT into R1 plus divided by R2. That means Vi is greater than VSAT. VSAT means 12 into R1 is 1.5 divided by 6.8. So that means the Vi should be greater than 2.647. Then only the VO goes to plus VSAT. So if we plot this curve, okay, so if we plot this curve over here, so suppose the transfer characteristics curve, so suppose this is Vi and this is VO. Okay, so what is the first condition? This is minus 2.647 and here the point is 2.647. So it is equally distributed, right, in the both the side of the origin. Okay, this is 647. So if Vi is less than minus 6.7, then VO will be minus VSAT. So if it is less than this, then it will become minus VSAT. Okay, understood, right? Yeah. And so previously it was plus VSAT and then it becomes minus VSAT. Sorry. So at first it was plus Vsat and now it becomes minus Vsat. Okay, so the direction will be in this direction. Okay, for the second case, what is happening, if Vi becomes greater than this, then it becomes plus Vsat. So it earlier it was minus Vsat and then it will become plus Vsat if it is greater than this. Okay, yeah. So this is the thing. So here we can see the hysteresis loop is in anti-clockwise direction, right? Opposite to clockwise direction, that is anti-clockwise direction. Anti-clockwise direction means it is a non-inverting Schmitt trigger. That means the input is applied in the non-inverting terminal. You can see also, you can verify also here that Vi is applying in the positive terminal, that is it is anti-clockwise direction hysteresis curve. Yeah, so this is the basic transfer characteristics, and here it is being asked that what is the upper and lower trip point. So upper and lower trip point will be, one is the upper trip point, V upper trip point, that is the UT. If we consider UT, this is 2.647, and VLT lower trip point is minus 2.647, or we can say plus minus 2.647. Okay, so the correct answer will be plus minus 2 plus 2.65, 647, that is 65. Okay, so this is the correct answer. Okay, now going to the next problem. In the Schmitt trigger circuit shown in the figure, the op amp is operating with plus minus Vsat equal to plus minus 15 volt. Okay, so here we are applying plus Vsat and here we are applying minus Vsat. So that means it is plus 15 volt it is applying, and it is applying minus 15 volt. Okay, so now what is happening, the Zener diodes have, this is a Zener diode, back to back two Zener diode combination here, and the on voltage of the diode is 0.7 volt and the Zener voltage of the diode is 9.3 volt. So what is the upper and lower tripling points or upper trip points? So we can easily determine this using the same Schmitt trigger analysis. So how we can solve this thing? So suppose, so there is a the op amp is in this condition, right? Okay, so what is happening, so here suppose this terminal is too much positive, so suppose VO is large negative, that means the current will flow from ground to this terminal. So if the ground to this terminal the current will flow, the D2, so the current I will flow from ground to V0, that means D2 is in on condition and D1 is in D2 is normally on condition and D1 is in breakdown condition, breakdown, because it is a Zener diode, right, as we have already discussed. So this is the P, this is the N, this is the N, this is the P. So too much negative voltage is applied across this D1, so D1 is in breakdown condition. So that means the equivalent circuit will become, so if it is VO, this is R3, this is RL, and then we can write the circuit as, so this will be negative, this will be plus, and similarly it is be negative, it will be plus. Okay, so this is 0.7 volt and this is 9.3 volt. So this is plus, this is minus, this is plus, this is minus, so VO will be stick to minus 10 volt. Okay, okay, in the second condition, if VO is large positive, then what happens, the D2 becomes in breakdown condition and D1 become in the on condition. That means the current will flow from V0 to ground and then the equivalent, so then the equivalent circuit will become, this is the R3, this is R3, and this VO, it is the RL, it is going to ground, this is VO, and here the D2 is in, at first the D1 is in normally on condition means it will be plus, it will be negative, and then again it is in breakdown condition D2, right? So it will be plus minus. So this is zero point 0.7 volt, this is 9.3 volt. So VO will stick to plus 10 volt. That means whatever be the whatever be the input voltage, the output voltage VO must be within the range of plus 10 volt to minus 10 volt. Okay, yeah. So now how we can solve this problem? So what is the upper trip point and what is the lower trip point of this? So suppose, so here we can see that whatever be the value of V1, that doesn't appears, the same value doesn't appears in VO, because if there is some there is a back to back two Zener diode combination in the opposite direction, so that limits the output voltage. So often this combination we can use in the circuit to limit the output voltage and stick to a particular voltage. So that means if there is this back to back two Zener diode combination with in opposite direction is there, then the VO value should be plus 10 volt to minus 10 volt. So now we generally solve this question. So suppose, so here similarly that V minus is equal to 0 volt in this op amp, this is V minus, and what will be the V plus? The V plus will be whatever is the Vi into, this is a superposition, by using superposition you can find out easily V plus. This V plus will be Vi into the using the voltage divider rule, R2 divided by R1 plus R2 plus, so at first we are considering this VO to be ground and Vi, sorry, yeah. So at first we are considering this Vi to be sorry, VO to be ground and Vi only one input is there. Similarly, uh, using the superposition, then again next consider the VO is only, we are applying only VO and Vi is grounded. Okay, so it will be VO into this will be R1 divided by R1 plus R2, right? Okay, so now the condition is case number 1, case 1, case 1, if VO is plus 10 volt, right? Because VO can vary from plus 10 volt to minus 10 volt. Okay, so if VO is plus 10 volt, then if V plus is less than V minus, if V plus is less than V minus, then VO, so case number 1 we can say, so suppose this is V sat, okay, V saturation is plus minus 15 volt, so plus minus 15 volt is applied. So case number 1 is in this circuit we can see this is VO1, right? So V1, if V1 is plus 15 volt, okay, so if VO1 is plus 15 volt, that means the VO is plus 10 volt, because there is a Zener back to back Zener diode combination. Okay, so that means this V plus minus V, if V plus is less than V minus, then V1 becomes minus 15 volt, as a result VO becomes minus 10 volt, right? Minus 10 volt. So this V minus V plus means, yeah, just wait one second. Yeah, so what is happening? Okay, so V plus, that means Vi into R2 divided by R1 plus R2 plus VO into R1 divided by R1 plus R2 if it is less than 0 volt. V minus is 0, right? This is 0 and this is this, okay, V plus. So if this is less than 0, that means Vi into R2 divided by R1 plus R2 is less than minus VO into R1 divided by R1 plus R2. These two cancels out, so Vi should be less than minus, VO is 10 volt, we have considered VO is plus 10 volt, right? So 10 into R1 divided by R2. R1 divided by R2 is how much? R1 is 1.2 divided by 8.2, right? 1.2 divided by 8.2. So if we use a calculator, 12 divided by 8.2, it is 1.46. So if Vi is minus less than minus 1.46, then only this VO becomes minus 10 volt. Okay, so this is the case. So similarly, if we consider the case 2, that is case 2, that is if VO1 is minus 15 volt, that means VO is minus 10 volt, right? So if now V plus is greater than V minus, then the VO1 becomes plus 15 volt. That refers the VO is plus 10 volt. Okay, so similar is the condition, V2 into R2 divided by R1 plus R2 plus VO into R1 divided by R1 plus R2. This should be greater than 0. So Vi into R2 divided by R1 plus R2 should be greater than minus V0 into R1 divided by R1 plus R2. So these two cancels out. So now Vi should be greater than minus VO into R1 by R2. So now what is the value of VO? VO is minus 10 volt. So this minus 10 and this minus becomes plus. So 10 into R1 by R2, that is 1.2 by 8.2. That means Vi should be greater than 1.46. So if it is greater than 1.46, then only this VO becomes plus 10 volt again, minus 10 volt to plus 10 volt again. Okay, so if we plot the curve, so if we plot the curve, if we plot this curve, this is the VO versus Vi. So if so this is 1.46 and this is minus 1.46. okay, so if Vi is less than minus 1.46, then VO will become minus 10 volt. So that means it is minus 10 volt. Okay, this is minus 10 volt and this is plus 10 volt, this is plus 10 volt. So this is the curve. So if Vi is less than this, then this becomes minus 10 volt from plus 10 volt. Okay, and similarly for this case, if Vi is greater than 1.46, if it is greater than 1.46, so earlier it was minus 10 volt, but now it will be plus 10 volt. So that will be like this. Okay, so this is the transfer characteristics curve. You can also verify that whether your answer is correct or not correct. I have already discussed you. So here the hysteresis loop is in anti-clockwise direction. See, the arrow is in from this direction to this direction, right? So this is the anti-clockwise direction. Anti-clockwise direction means there should be non-inverting Schmitt trigger. So that means the input is in the non-inverting terminal. You can also see the input Vi is in the non-inverting terminal of the op amp. So that means this answer is correct. And so what was the question, that what should be your upper trip point and lower trip point? So the upper trip point and lower trip point is, this is the upper trip point and this is the lower trip point. So this is the value is plus minus 1.46. So this is the answer, plus minus 1.46. And what is the hysteresis width if it is asked in question? So that will be 2 into 1.46, right? Here it is 1.46, here it is 1.46. Okay, so that is the hysteresis width. So the correct answer will be plus minus 1.46. Yeah. Okay, the next question. In the circuit of the same question, what is the minimum value of R3 required to limit the op amp output current to 5 milliampere? So the current, that is, if so there is two condition. One is VO can be 10 volt, this is case 1 I am considering, and then only the VO1 will be 15 volt. And case number 2, this VO is minus 10 volt and V1 is minus 15 volt. Then what is happening? What is the value of R3? So that means this VO1, then the current will flow from this side to this side for case 1. So case 1, the current I will be, if it is considered I will be VO1 minus VO divided by R divided by R3. This is the resistance, right? So it is 5 milliampere equal to 15 by 5 divided by R3. Sorry, 15 minus 10. VO is 10, right? Yeah, VO is 10. So that means R3 will be 5 divided by 5 milliampere, that means 1 kilo ohm. And in the second case, what is happening? Now VO is minus 10 volt, it is at higher potential, and V1 is in the lower potential, minus 15 volt, then the current will flow in this direction, right? So this current will be VO minus VO1 divided by R3. VO is minus 10 minus of minus 15 divided by R3. So that is 5 milliampere is equal to 5 divided by R3. That means R3 will be 5 divided by 5 milliampere, which refers to 1 kilo ohm. So the value of R3 required is 1 kilo ohm. So option A will be correct to limit the output op amp current to 5 milliampere. Okay. Yeah. Okay. So I am moving forward to the next question. So which of the following statements is true about the oscillator circuit shown in figure? So if you have any question, then you can ask. So here here it is asked that which of the following statement is true about the oscillator circuit shown in the figure. So this is a basic oscillator circuit, we can see. So we will analyze this circuit. Okay, so if we divide this circuit into two parts, suppose if we consider this circuit in two parts, then we can see this is a negative feedback circuit, and here it is a positive feedback circuit, because here the output is faced to the, or out the feedback path is in between to the output to the negative terminal, output to the negative, or the inverting terminal of an op amp. Okay, and here the output is faced to the here there is a feedback path in between the output terminal to the non-inverting terminal of an op amp. So this is a positive feedback, and the previous one is the negative feedback. Okay, so which are the following statements true about the oscillator circuit shown in figure? So in this oscillator circuit, we can see that, so this positive feedback circuit, so at first we will consider this circuit. Okay, so this circuit I am drawing, suppose, so this is a VO1, so this is VO1, this is 1.2k, that is R1, and here it is VO2, this is R2, this is 6.8k. Okay, yeah, and there is some RL which is 1k. Okay, yeah. Okay, so this circuit I am considering it at first. So this is a positive feedback circuit, so basically this is a Schmitt trigger, Schmitt trigger circuit. Okay, so how to analyze this circuit? See, so we have already solved this thing, the Schmitt trigger problem. So like this only we have to solve. So here V minus is equal to 0, this is V minus and this is V plus, and V plus we can determine using the superposition theorem. At first we consider only VO1 to be active and VO2 is ground, so this V plus will be VO1 into R2 divided by R1 plus R2, right? Okay, and then plus consider this VO2 to be active and VO1 to be grounded, so plus VO2 into R1 divided by R1 plus R2. Okay, so this is the thing, R1 plus R2. And now case number 1, consider this VO2, the output is in saturation region, that is plus Vsat. So suppose there is plus Vsat DC bias and this is minus Vsat, DC bias is applied. So if VO2 is plus Vsat, then if this V plus is less than V minus, then this output will be minus Vsat, VO2 will be minus Vsat. So that means VO1 into R2 divided by R1 plus R2 plus VO2 into R1 divided by R1 plus R2, if it is less than 0, then VO2 becomes minus Vsat. So that means VO1 into R2 divided by R1 plus R2 is less than minus VO2 into R1 divided by R1 plus R2. So this two cancels out, so VO1 should be less than minus VO2 into R1 by R2. That means this VO1 should be less than minus Vsat into R1 divided by R2. Okay, so this is the case 1. Okay, similarly if we consider the case 2, so what is happening in case 2, suppose this VO2 is equal to minus Vsat. Okay, so now if, that means if V plus is greater than V minus, then only this VO2 becomes plus Vsat. Okay, from minus Vsat to plus Vsat. So now we can write VO1 multiplied with R2 divided by R1 plus R2 plus VO2 into R1 divided by R1 plus R2 should be greater than equal to 0. That means VO1 into R2 divided by R1 plus R2 should be greater than minus VO2 into R1 divided by R1 plus R2. These two cancels out. That means VO1 should be greater than minus VO2 into R1 divided by R2. That means this VO1 should be greater than, now VO2 you consider it as minus Vsat, so that will be minus and minus positive number, so plus Vsat into R1 divided by R2. So this is the another condition. Okay, yeah. So this is the first part of, this is the second part of the whole circuit. So we have considered only Schmitt trigger part, that is the positive feedback part. Now we should look into the first part of the circuit. Okay, yeah, just a second. Yeah, so in the first part of the circuit, how it is given? So the first part of the circuit is minus plus, so this plus goes to ground, there is some value which is R, this is 5k, and then here we have VO1 and this is VO2, because this is connected to this, right? VO2 is being applied. Okay, and this is 5k and this is C, and this is very interesting problem, C. Okay, C means it is 0.2 microfarad, 0.2 microfarad. Okay, yeah. Now, how to solve this? Okay, so now this is a basically negative feedback circuit, negative feedback circuit, negative feedback op amp. This is the first condition, and second, there is no non-ideality, so it is an ideal op amp. So as we have already discussed in the earlier classes, the virtual short concept holds, virtual short concepts hold. That means V plus is equal to V minus. Okay, so now as V plus is equal to 0, so V minus will be also equal to V plus equal to 0, right? So that means V minus is also, this is also ground, that is 0 volt, this thing. So whatever the current flowing in this direction, that current will flow in this direction also, right? So we can write this current I as VO2 minus 0 divided by R is equal to this current, the current flowing through the capacitor, we can write as C dVdt, C d dt of V, that is if the current flowing in this direction, so the current is flowing in this direction because no current will flow through the op amp, right? You already know that. So this is direction, so that means this is plus and this is negative, this is plus and this is minus terminal, positive and negative terminal of the capacitor. So that means C of 0 minus V0, this is 0 and this is V0. So that means VO2 divided by R is equal to C of d dt of minus V0, minus V0. So if it is d dt of minus V0, that means VO2 is equal to RC minus RC dV0 dt. Okay, so that means dV0 is equal to minus 1 divided by RC. Now resistor and capacitor have some fixed value. Okay, so dV0 is equal to minus RC into VO2 into dt and integration of that. So that means VO, so if we consider it as, so it will be minus 1 by RC because R and C has a constant value, integration of VO2 into dt. So this is VO1, right? This is minus VO1, this is VO1, this is VO1, this is VO1, this is VO1. Okay, so that means VO1 of T is equal to, so if we integrate this equal to, so whatever we are getting, that is minus VO2 is a constant fixed value because VO2 either go to plus V set or minus V set. So minus VO2 divided by RC into T plus the initial value of this. So V1 I am considering is as T dash, the initial value. So this is the equation of the VO1. Okay. Okay. So what is the given question? Question, the VO2, VO1T and VO2T, if we plot with respect to time, then how the it will look like. Okay. So so if we plot VO2T with respect to T's, see one thing, now we are plotting the VO2T with respect to time, not with respect to input. Okay, if it is plotted against the input, then it is known as transfer characteristics, but now it is the simply time domain. So what will be the output? Suppose the VO2 is plus V set, and after certain time it will go to minus V set. Again after some time it will go to plus V set again, and then it will go to minus V set, and like this it will go. Okay, and what will be the what will be the this thing, the diagram of this thing, VO1T. So V1T is basically, so see one thing, if VO2 is plus Vsat, then the slope of this, in this equation the slope is Vsat divided by RC. It is plus Vsat, so it will be minus Vsat into RC, this multiplied with T. That means if it is positive, then it will go down. Okay, and after that, if it is negative, if VO2 is minus Vsat, when it transfer to minus Vsat, then the slope will be plus Vsat divided by RC, that is the positive slope. So it will again go to positive slope, then again it will go to negative, and then again it will go like this. So this is the thing. Okay, so this thing is VO1T. So if we consider this thing VO1T, so so how we can find out this value? This value is what is this value? We can say that if if here VO2 is, at first VO2 is plus Vsat, so if it is minus Vsat into R1 minus R2, if it is less than that, then it will become minus Vsat, minus Vsat. So it is minus Vsat into R1 by R2, this is minus Vsat into R1 divided by R2, and similarly this thing is plus Vsat into R1 by R2. Okay, so this is diagram. So according to the given question, so this VO1T will be triangular and O2T will be squared wave, right? So the correct answer will be option C. The VO1 is a triangular waveform and VO2 is a square waveform. Okay. Okay, if we move forward to the next question, in the Schmitt trigger circuit shown in the figure, plus minus Vsat is plus minus 15 volt for the op amp. So what is the oscillation frequency? For the same problem, we need to find out now the oscillation frequency. Okay, so how to find out the oscillation frequency? So yeah, so I am plotting this thing. Okay, yeah. Okay, so what is the oscillation frequency we need to find out? Okay, so what is the oscillation frequency we need to find out? So this is the waveform basically. So whatever we got in the previous equation, I am writing this. If VO1 is greater than Vsat into R1 by R2, if VO1 is, so first condition is if VO1 is greater than Vsat into R1 by R2, then VO2T will be equal to minus Vsat. Second equation is if VO1 is less than minus Vsat into R1 by R2, then VO2 is plus Vsat. And the third condition, what we got, this VO2, this VO1 is basically minus 1 by RC. So VO1 is basically minus 1 over RC integration of VO to dt. That means VO1 at any particular time is equal to minus RC VO2 into T plus it has some initial value which is I am referring as T dash. Okay, V1 T dash. So these are the three equations. So analyze the output waveform first. So this is VO2T. So VO2T is at first plus Vsat. So it is in the plus Vsat condition. And now what is happening? Whenever the VO1, so when so we so here from this equation you can write when VO2 is plus Vsat, then VO1T is equal to minus 1 by RC into Vsat into T plus VO1T dash. That means the slope will be, the slope of the curve will be, slope is minus Vsat divided by RC, right? This multiplied with T, that means this is the slope. So which is a negative number, because Vsat is a positive, R and C is also positive, which is a negative number. This is case A, right? And case number B is when VO2 is equal to minus Vsat, then VO1T, if we put is minus Vsat, then it becomes 1 by RC, minus minus becomes plus into T plus VO1 T dash. Okay, and then the slope will be equal to Vsat divided by RC, so which is a positive slope. Okay, so let's analyze this problem and analyze this diagram. So VO2 is at first it's in plus Vsat, so it was in plus Vsat, and if this and plus Vsat, this is the first thing. And then what happens if V1 is less than minus Vsat by R1 by R2, that means if it goes beyond this thing, then it changes, then this VO2 changes to plus Vsat, sorry, yeah, then this VO2 changes from minus Vsat to plus Vsat. Okay, so if VO1 is at it sorry, if VO1 is in Vsat, sorry, VO2 is in Vsat condition, then what is happening? If VO1 is greater than this thing, that means R1 minus R2, then it becomes minus Vsat. So once it becomes minus Vsat, so what is happening? When it has minus Vsat condition, then the slope was in positive direction, that is this is the positive direction, slope is in the positive direction. And whenever what is happening, whenever it becomes greater than Vsat into R1 plus R2, whenever it gets become, then only this VO2 switches from plus Vsat to minus Vsat. Okay, this is a minus Vsat, it transfer to the minus Vsat. So this is the thing. Okay, yeah, so now it is being asked that what is the frequency of the signal. So frequency, to find out the frequency, so this is the time period, so we need to find out the time period. And as this is the same thing, that is the Vsat into R1 plus R2, and it is minus Vsat R1 plus R2, so it is symmetric about the origin. If we plot the hysteresis curve, that means this T1 and T2 is identical, this is T1, and if we consider this as T2, then T1 and T2 is identical, that means T is equal to nothing but 2 into T1. So now we need to find out the value of the T1. Okay, so what is the value of the T1? How we can say? We can say from here, that is, so this is changing from this to this, so that means so this is the final value, that is minus Vsat into R1 minus R2 divide minus of this thing, right? So y2 minus y1 divided by x2 minus x1 is equal to the slope, right? So y2 minus y1 is Vsat into R1 by R2 divided by divided by the time period, that is t1 minus 0, that is t1 is nothing but the slope. The slope is what? Slope is minus vsat divided by rc. Okay, this is the negative slope. Okay, so what is happening? Minus 2 into vsat into r1 divided by r2 divided by t1 is equal to minus vsat divided by rc. So this minus minus cancels out, vsat cancels out. Okay, so what is there? 2 into r1 by r2 into rc is equal to t1, that is t1 is equal to twice rc into r1 by r2. So what is the value of time period? Time period is nothing but 2 into t1 equal to 4 into rc into r1 divided by r2. This is the time period. So frequency is nothing but 1 divided by time period equal to 1 divided by 4 into rc into the, so here it will be r2 and here it will be r1. Okay, so this is the formula of the frequency of the oscillation. Okay, so if we put the value of this register element, so what we are getting? So frequency f will be r2. What is the value of the r2? R2 is nothing but 6.8 kilo ohm, right? 6.8k and 1.2k. So it will be 6.8k divided by 4 into 6.8k means 6.8k, 4 into r into c, r and c. What is the value of r and c? 5k and 0.2 microfarad. 5k into 0.2 into 10 to the power minus 6 into r1. R1 is how much? R1 is 1.2k, right? So it will be 1.2 into 10 cube. So this things cancels out. So it will be 6.8 into 5 and 0.2 makes 1. So that means 4 into 1.2 into 10 to the power minus 3. That means 6.8 divided by 4.8 into 10 cube. That means 6.8 divided by 4.8, this much kilohertz. So what is the answer? So this is 6.8 divided by 4.8. So that will be 1.416. So 1.416 kilohertz. So this is the answer. So this is the frequency of the oscillation. So the correct answer will be 1.42 kilohertz, right? Option D. Okay. Okay, fine. In the next question, what is, so it is the same circuit, it is asked the same circuit, but now the R1 value changes to 1 kilo ohm, right? So then it is asked what is the oscillation frequency. So we have already derived. So f is equal to what is, f is equal to this thing, right? F is equal to R2 divided by 4 into RC into R1. Okay, so now what is the value? So this R2 is basically 6.8 kilo ohm 10 cube divided by 4 into R means 5k, 5 kilo ohm into C is 0.2 into 10 to the power minus 6, okay, into R1 now it changes to 1 kilo ohm. So 1 into 10 cube, okay. So this 10 cube cancels out, 5 into 0.02, that makes 1, So 6.8 divided by 4 into 10 to the power minus 3, that is 6.8 by 4 into 10 cube hertz, that is 6.8 divided by 4 kilohertz. That means 6.8 divided by 4, it is 1.7. So it is 1.7 kilohertz. So the correct answer will be option B. Okay. So see, if we want to change the oscillation frequency, then easily we can change it using by varying the circuit elements. Maybe so it can be R1 or it can be R2 or it can be R or it can be C. Okay. In the next question, in the oscillator circuit R2, now R2 is changes to 10 kilo ohm with all other component values same as the question 8. So what is the oscillation frequency? Okay. So now as we have already discussed, this thing is equal to R2 divided by 4 into RC into R1, right? So now what is the value of R2? It is 10 kilo ohm. 10 kilo ohm means 10 into 10 to the power 3 divided by 4 into R into C, right? So R is 5 into 10 cube, C is 0.2 into 10 to the power minus 6, and what is the value of this R1? So the R1 is 1.2, right? 1.2. So now 5 and 0.2 cancels out, and this is 1.2 kilo ohm. So these two also cancels out. So now it will be 10 divided by 4.8 into 10 to the power minus 3. That is 10 divided by 4.8 into 10 to the power 3, this much hertz. That means 10 divided by 4.8 kilohertz. So it will be 10 divided by 4.8. It is 2.08 kilohertz. So the correct answer will be 2.08 kilohertz. Okay. So this is the answer. Okay. So now in the next question, in the same oscillator circuit, now we are changing the value of R with all other component values same. So what will be the oscillation frequency? So it is also the similar thing. F is R2 divided by 4 into RC into R1. Now the R2 value is 6.8 into 10 cube divided by 4 into RC. R is changes to 8.2 kilo ohm, right? And this is 0.2 into 10 to the power minus 6. Okay, C value. And then what is the, and then sorry, RC into R1. What is the value of R1? It is 1.2. Okay. So now what is happening? So this 10 to the power 3, 10 to the power 3 cancels out. And now if we calculate the value, 6.8 divided by 4 into 8.2 into 10 cube into 0.2 into 1.2 to 10 to the minus 6. Yeah, so it will come as 0.864 this much kilohertz. So that refers to 864 hertz. So the correct answer will be option A. Same thing, right? Now in this question it is asked, in the oscillator circuit of question 8, the supply voltage is reduced such that the Vsat changes from 15 volt to 10 volt with all other component values same in question 8. So what is the oscillation frequency? So we know the F is nothing but whatever we derive, R2 divided by 4 into RC into R1. So we can see that the F is, that is the frequency is independent of Vsat. So there is no Vsat in this equation of frequency, right? So irrespective of the Vsat, the frequency will be the same. So whatever we have obtained in question number 8, the frequency, this is 1.416 kilohertz. The same thing will apply here, and this is the same thing, 1.42 kilohertz. So this will be the correct answer. So you can also see by using this thing, this diagram. So if the vsat is reduces, if the vsat is reduces, so that means the scale of this thing will only reduce, right? It will be plus vsat, and then this point will be this point will be this, and this point will be minus vsat, will get reduced, right? So that means the scale will only reduce, but the frequency will be the same. So we can changes the value of the square waveform or the triangular waveform by varying the vsat value, right? And we can change the value of the frequency of these two waveform by varying the component value, that is the r value, c value, r1 value, and r2 value, right? Okay. Okay. uh, so I am moving to the next question. Okay. The circuit in the figure is an oscillator based on the Barkhausen criteria. So what is basically oscillator? Oscillator is basically something where when there is a positive feedback in any circuit, then it becomes an oscillator. Oscillator means without the input, the output becomes to oscillate. That is the oscillator concept. Okay, the concept of the oscillator. So suppose, so suppose there is a system. Okay, so this is a system, and this is some input, and this is going to some output VO, and certain part, this is known as a feedback. So if it is, the gain is A and this gain is B, so this is the VI, that is the input, and then we are adding some of the part of this to this. Okay, so if there is a system, this is a mixer means that will mix the two signal. So suppose if we put any input Vi and the system has gain A, then the output VO will be, if it is in frequency domain, then we can write the VOS, it is A times VIS if there is no feedback, but certain amount of VOS is being feedback to the input, and then it adds with that this input signal, and then that is being that is multiplied with the gain, and the output becomes more. So that means without, if any certain time, if we make this VIS is equal to 0, and initially it starts something, means if initially it has certain small amount of voltage, then that will be amplified and that will be fed again to the system, and then the gain will be more, and then some part of this again fed to the input, and then the gain will be even more. So like that it will the output will getting generated without the applying any input voltage, or without applying any input. So this is the basic concept of the oscillator. So the oscillator must be in the positive feedback. So here it is the positive feedback, so it must be in the positive feedback. Okay, yeah. So here actually the VOS divided by VIS can be written as 1 divided by 1 minus AB, that is the gain of the forward path and gain of the feedback path, 1 minus AB. Okay, so this is the thing. Okay, so now uh, so what is happening, so as it is in the positive feedback, so that's why it will be minus sign, it is a negative sign over here, but if it is a negative feedback, then it will be positive feedback over here. So now as the oscillator starts to oscillate without the input, so that means that VIS is equal to 0. So that's why VOS divided by VIS becomes VOS divided by 0, that means the infinite. Okay, so it starts to oscillate. Okay, so it is infinite. So if we put VIS equal to 0 and equate this equation, then we get 1 minus mod AB is equal to 0, that means mod of AB is equal to 1. So this is the basic concepts. So And also one more thing, it is a into b, so ab is equal to 0, that means mod of ab is equal to 1. So ab is equal to 1, that means the mod of ab is equal to 1. And one more thing, angle of ab should be 0 degree. These are the two basic conditions regarding the oscillation of the system. If any system satisfy these equations, that is mod a b is equal to 1, this is first condition. And the second condition of angle of AB is equal to 0 degree. This condition refers to Barkhausen criteria. Barkhausen criteria. Okay. So then the system is said to be the system is said to be an oscillator. Okay, so the circuit in the figure is an oscillator based on the Barkhausen criteria. That means mod AB is equal to 1 and angle of AB is equal to 0 degree. The gain limiting network is not shown. Okay, so that is not needed here. So now it is asking that when it starts to oscillate, the oscillator starts to oscillate, what is the oscillation frequency? With R is this and C is this. Okay, so to operate this as an oscillator, so these two condition has to be satisfied. So now we will interested in these two things, that how we need to find out these two things. Okay, so A and B. Okay, so suppose if we want to find out the value of A from this diagram, how we can find out? We can find out simply from this diagram. If we want to find out, so that means, so it is a mixture, and here it has A, and it is VO of S, and it has Vi of S. Okay, this thing. And then again we have some feedback path B, and if we disconnect this path, that is, it is disconnected. If we disconnect this path, then whatever will be the VOS divided by VIS, that will be the A, right? So VOS divided by VIS, that will be the value of A. Now how we can write out what is the value of A? So we should remove the other part. That means we should remove the feedback path. Okay, so if we remove the feedback path from this circuit, minus plus, so this is R1. So here the input is equal to 0. See, because without the input it starts to oscillate, so this is basically equal to 0. So if we put Vi over here, that is equal to 0, and here also, okay, so R1 is basically in grounded, and here it is Vi, that is the input to the positive terminal. Okay, so if it is Vi and this is R1 and R2 and this is VO, then we can find out what is the value of this thing. So this VO, this is a negative feedback, and also it is a ideal op amp, so virtual short concept holds. And as we have already discussed, this is the non-inverting op amp. Non-inverting op amp means non-inverting op amp, that means the output, the negative output, there is a negative output is already said, but non-inverting op amp means the input is applied to the non-inverting terminal of an op amp, so it is a non-inverting op amp. So non-inverting op amp, what is the output? VO divided by Vi, it will be 1 plus R2 by R1, we have already determined, right? How we can find out? We can find out here also, it is, if it is Vi, so that means here the current flowing through this will be Vi divided by R1, and the same amount of current will be flow through this. So this terminal is Vi, so VO will be Vi, and there will be certain drops, so that will be plus Vi into R2, Vi by R1 into R2, right? So if we take this common, 1 plus R2 divided by R1, that means VO divided by Vi is equal to 1 plus R2 by R1. This is a common non-inverting terminal. We have a non-inverting amplifier. We have already discussed this in here. Okay, so this is the normal this thing. So this is the A. So A is basically 1 plus R2 divided by R1. Remember this thing. Okay. Okay, so now we need to find out what is the value of B. Now from this thing, how we can find out the value of B? So we can find the value of B if, suppose, this is the thing, here it has A, and here it is V out, and here it is B. So whatever we are giving V out, the V out, if we fetch it as V in and we get it as Vx, then we can say Vx divided by V in is equal to B, right? Vx divided by V in. So now here also, if we redraw this circuit again, what we get? So minus plus, okay, so this is VO, and here if we consider is VSX, it will be 1 by SC, right? And R will be R. Similarly, it will be 1 by SC, it will be R, and sorry, and this is nothing but V plus, and sorry, it is the VXS, and if we consider it as V1, V1S, this is V0S, then what we can write? So here we can write the current flowing through this plus this is equal to 0 according to the KCL. So V1S minus VXS divided by 1 divided by SC. So okay, so basically if we okay, so here whatever the current that will flow from this side, and this will flow from this to ground. Okay, so VSX divided by R, this amount of current is flowing through this, so that means V1S minus 0 divided by minus 0, V1S minus 0 divided by R plus 1 by SC, plus VIS divided by 1 by SC, plus V1S minus V0S divided by R is equal to 0. So that means SC V1S divided by 1 plus SCR plus SC V1S plus V1S divided by R is equal to V0S divided by R, V0S divided by R. So now if we take V1S common, and if we multiply it with R, then we get VOS is equal to VOS, this thing is equal to SCR divided by 1 plus SCR into V1S plus SCR into V1S plus V1S. So if we take common of V1S, then we get SCR divided by 1 plus SCR plus SCR plus of 1. Okay, so this much we got. Okay, so now so this is the VOS equal to V1S into this, and now VSX, this is VSX, this is nothing but if we, so if this is VIS, so VIS into, simply if we use the voltage divider rule, R plus 1 by SC, that will be VSX, right? That will be VSX. So V1S into SCR divided by 1 plus SCR is equal to Vs of x, then V1 of S equal to 1 plus SCR divided by SCR into Vs of x. Okay, see, now in place of VIS we put this thing VSX, so VOS is equal to 1 plus SCR divided by SCR into, here it will be 1 plus SCR, here it will be SCR plus 1 plus SCR total whole square into VSX. So now this 1 plus SCR cancels out, and this is 1 plus SCR whole square plus 2 SCR plus 1 SCR is this, divided by SCR into VSX. Now we need to find out VSX by V0x, right? Vx versus by B is equal to B, right? So B will be Vsx by V0s, that will be SCR divided by 1 plus SCR total whole square plus 3 SCR. So this is the B. Okay. Now if we need to find out the oscillation frequency, it need to be satisfied the Barkhausen criteria. So according to the Barkhausen second criteria, first criteria is mod of AB is equal to 1, it is first, and second is angle of AB is equal to 0. So if we consider angle of AB, so A is what we have got, like 1 plus R2 divided by R1, this we got, and B is nothing but this. So angle of A plus angle of B is equal to 0. Angle of A is tan inverse 0 because there is no term, divided by this thing, plus angle of B. Angle of B we can say j omega CR divided by 1 minus omega square C square R square plus 3 j omega CR, right? So here, so this angle of B is equal to 0, but this terms that is equal to 0, that means angle of B should be equal to 0. So here we can easily see that B will be a real quantity, B will be a real quantity if 1 minus omega square C square R square is equal to 0. So if it is 0, then B will be j omega CR divided by 3 j omega CR. So these two cancels out 1 by 3, then angle of B will be equal to 0. That means this condition has to be satisfied. If this condition has to be satisfied, that means omega square C square R square is equal to 1. That means omega equal to 1 by RC. That means F equal to 1 divided by twice pi into RC. So this is the condition or the frequency of the oscillation of the oscillator. Okay, so now R and C is 6.8K 47 nanofarad, 6.8K 47 nanofarad, 6.8K 47 nanofarad. So what is the frequency of the oscillation? That is the question, right? What is the frequency of the oscillation? So it will be so 2 into pi into 6.8 into 4.7 into 10 to the power minus 6 divided by. So here it will be 4979.81 hertz. That means 4.97 kilohertz. So 4.97 kilohertz. The correct answer will be, sorry, I think I have mistaken something. Okay, I'm calculating this thing once again. So 10 to the power 6 divided 2 divided by 6.8. Oh, this is coming to be 497. Sorry. So this is coming 497 hertz. 497 means almost equal to 500 hertz. So the correct answer will be option D, 500 hertz. Okay. So moving forward to the last question, for the oscillator, same oscillator, what is the minimum value of R2 by R1 required for the circuit to oscillate? So we have found out that to oscillate the circuit, omega should be equal to 1 divided by RC, or frequency will be 1 divided by twice by RC. Then according to the Barkhausen criteria, mod of AB will be equal to, and this also need to be 1, mod of AB need to be 1. So if mod of AB should need to be 1, then A is nothing but 1 plus R2 divided by R1, this thing, and B will be 1 by 3, as we have already found out, 1 by 3 into 1 by 3, this needs to be 1. That means 1 plus R2 by R1 by R1 is equal to 3. That means R2 by R1 needs to be 2. So the value the option the correct option will be option B. So the value of the R2 by R1 should be 2 in order to oscillate. So these are the two things, the Barkhausen criteria, and if both of these options satisfied, then only we can say that it will the circuit will oscillate, okay, or it will behave as an oscillator. Okay, so that's all for today. So we will again meet in the next Tuesday from 6 p.m. So thank you all. Okay, I am ending the meeting.